here's a crazy function, x to the x. Right? If I plug in f at 1, I get 1 to the 1, which is just 1. F at 2 is 2 to the 2 is 4. F at 3 is 3 to the 3 is 27. This thing is crazy. Next we'll do 4 to the 4, and it's going to be like way bigger. So this function's nuts, and we're going to think about it in terms of its domain being the positive numbers, and we're not going to deal with what happens when you try to feed negative numbers into this expression. As with most of the functions that we're dealing with in this blob of content, we'd like to take the derivative of this function. I want to take the derivative of it. So we have some options for things to do. And I think I want to first approach other functions, because I've got like an x downstairs and upstairs. So like maybe we should try to think about, let's let g of x be some number b to the x. And then we can approach that right there. All right. If this was e, then we'd know how to take the derivative of it. But b isn't e. B is just the base. It's just a placeholder. So it's some number to the x. We like to take the derivative of this expression. There are a bunch of different ways that we could approach this, but I'm going to approach this by realizing that b is equal to e to the natural log of b. Right? Because x above and the natural log functions are inverse functions of each other. And I already know how to take the derivative of e to the. So I'm just going to rewrite this g of x as an e to the function. So this is going to be e to the natural log of b times x. Nice. Okay. Well, now the chain rule is going to be in effect. I've got an e to the. So g prime of x is e to the natural log of b times x. And now I need to chain out the derivative of the inside right here. That looks a little not clear. Let me go ahead and make that a little bit more clear. That's the natural log of x, which sometimes you just see written as log without a base. I prefer ln. So I need to chain out the derivative of this natural log of x right here, and the derivative of natural log b times x is just natural log of b, and then it's canonical to put the stuff that's not inside the exponential function in front of it, so we don't accidentally stuff it inside when we evaluate. So this is natural log of b times e to the natural log of b x. And now if you really want to get rid of the stuff inside here and return back to something that looks more familiar with respect to the original function right here, this is natural log of b times b to the x. Okay. So now you know how to take derivative of arbitrary things with some fixed base down here. So let's kind of do the same thing for this x to the x function. So we're gonna realize the same thing right here, that there was nothing special about b. That's just some number. So I might as well have x right there. So I'm gonna wipe this content out so I'm not walking through it. Okay, so using this realization that x is e to the natural log of x, we can rewrite f as e to the natural log of x times x. And now we're in the clear, because I can take the derivative of this expression right here, because it's just e to the something, and I don't have to deal with everything inside of there, because it's just a product of a natural log, and I know how to take the derivative of natural logs. So f prime of x is equal to e to the natural log of x times x. And now I've got to chain out the derivative of the inside there. So I'm going to do a little placeholder here and go natural log of x times x prime. I am off screen. Why am I writing so far to the right today? I don't know. I'm just going to move over to the left and chain out to the left. Multiplication commutes, so I can totally do this. So this is going to be x natural log of x prime. That's what f prime of x is equal to. So now we need to apply this prime to this expression right here. That's a prime. Apply it to this expression right here. So that's a product rule on that because it's a times. So let's do 1 times natural log of x plus x times 1 over x times e to the natural log of x times x. And then let's simplify and let this be natural log of x plus 1 times x to the x. So the derivative of the crazy function x to the x ends up being like not that completely crazy. In some sense, it's predictable that you're going to end up with the same thing in the function again because it's an exponential function. And then the scaling factor is just not constant because the base wasn't constant. Yeah. So that's the derivative of x to the x. And I think I'm going to call it good there. So thanks for watching, and I hope you have a nice one. Bye.